Yo, 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 Math by the Moon, back with another video today. Had to represent one district, one community, Williamsport Millionaires. That's what it's all about. We're going to talk about reflections of square root and cube root across the x-axis, and we're also going to talk about dilation, which would be the vertical stretch or the compressions that we're going to see. All right, so let's start it off. You ready? Ooh. So here is the basic look of, first of all, the parent function for the square root of x here in red. Here's our parent function table. Y equals the square root of x. So we plug in our perfect squares into this one, right? Plug in a 1, 4, 0, 0, 1, 4, 9, 16, 25, and so on, and we can do the square root of it. Now, if I have a negative right there where the a is, so we've talked about the h and the k and how the h slides it left or right and the k slides the point up or down for the y's. If I have a negative in front of this, what really ends up happening is I have this square root of x that I'm going to be multiplying by a negative. So if you think about it, it's our output. It's going to be our y value that we're multiplying by a negative. So what once was a positive 1 is now going to be a negative 1, or a positive 2 is now going to be a negative 2. 3 is now going to be a negative 3 when I plug it in here. Because I'm going to do the square root of my perfect squares, then multiply it by a negative. So the y values aren't going to be these, they're going to be these, but with a negative sign in front of them. So that's what happens with this guy right here, this leading coefficient. If he's negative, he's going to reflect them across the x-axis. Now, it's a reflection across the x because the y value, what once was 1 is now negative 1. What once was 2 is now negative 2. And if you think about that movement that it's actually taking place, it's actually going from one side of the x-axis to the other, okay? Which means it's changing the y value. The x value stays the same because you're still on the same vertical plane. The y value is flipping across. So the cube root is no different. Here's all your perfect cubes right here. And you can see the red one here is our perfect parent function, it's our parent function. So take 0, 0 is not going to change because anything times 0 is still 0. But let's take the parent function 1, 1, and let's plug in a 1 right here, and then you'll get a 1, but then it'll be multiplied by a negative, so it'll be a negative 1. And this 2 will then be a negative 2. So you can see how it's still on the same x plane, still at 8, still plugging in 8 and getting a negative 2 now because of that negative sign right there. So that is the leading coefficient in front of a radical will reflect the y. It will change the y to the opposite sign, reflecting it over the x-axis. So then the next thing we got to look at would be, well, okay, so it's negative. We know it's going to reflect the y. It's going to go across the x. What if it's got a number attached to it? Well, it's technically a multiplier, so it's going to be multiplying by a certain amount then. So we do the square root, we get our parent function resulting outputs, and then we got to multiply it by this number here. Okay, and after we multiply it by that number, then we have to add this number here if there happens to be a number. So if we look at these, right here, our parent function 1, 1, 4, 2, and so on. If I take this 2 and multiply it by the answer to each one of these, so instead of we're still plugging in a 4, but then we're going to multiply it by 2, so now my y values are going to be double. So on the blue one, it's going to be at 4, 4, or 1, 2 instead of 1, 1. If I take and cut it in half, that's called a vertical stretch when this is a greater than 1 number, a vertical stretch. What threw me off, I'm sorry, what threw me off was my kids, and then that's a cube root parent function table, and I want the square root function table over here. Yeah, see, I'm looking at that and I'm thinking, what did I do wrong? Anyway, so back to our square root. Let's say we do the square root of all of our perfect squares, 0, 1, 4, 9, 16. We know the answer is 0, 1, a 2, a 3, a 4. And every single one of these, we're going to have to cut in half. So instead of, well, 0, 0 is going to be the same, but instead of 1 comma 1, it's going to be 1 comma 0.5. It's half as high. That's a vertical compression. We've compressed the height downward by a factor of a half. So every single y value for the parent function, which is this guy right here, we've cut in half, right? So this 9 would be at 1.5, if I could just keep going out. So you got your reflections, and you also have your dilations, which would be either a vertical stretch when it's greater than 1, when this number is greater than 1, or a vertical compression when it is between 0 and 1, okay? So now let's get into the main business of this, all right? Let's do a complete transformation with a vertical stretch or compression and maybe even a reflection, okay? So I have the parent table here, 0, 1, 4, 9 for square root. And I have this new function that I have written here. It has an x minus 4 plus 3 and a 2 out in front. So what we talked about before is minus 4 really means add 4 to all of these guys. So I'm going to take this and I'm going to write down a 4. I'm going to write down a 5. I'm going to write down an 8. I'm going to write down a 13, right? That'll be enough for now. And over here, what I actually have happening is there's two things that are going to happen. I'm going to do the square root of this first. Then I'm going to multiply by 2 because of order of operations. And then I'm going to add 3. So technically what I'm doing over here is 2 times y plus 3. And I'm stealing the y's from up here, right? And this one, all we did really to these x's was instead of minus 4, we really kind of added 4 to this table here to get our real input values. So again, that's 2 times the y plus the 3. 2 times 0 is 0, plus 3 makes this 3. So 4 comma 3 should be a point on our graph. 4 comma 3, it is. It's right there. Perfect. And then I'm going to stick with blue. So I should take this and multiply it by 2 and add 3, right? So that'd be 2 plus 3 would make this 5. So 5 comma 5 should be on there. And it is. Now, let's run through one of these. Let's say, make sure we understand why. I'm taking this 8 and I'm plugging it in here, right? 8 minus 4 is 4. The square root of 4 is 2. 2 times 2 is 4. And 4 plus 3 would be 7. Now, do the shortcut, since I showed you what's actually happening, is you're doubling the old y, the original parent function y, plus 3. Take, where were we here? We were at this one, right? So take 2 times 2, which is 4, plus 3, which is 7. That's a little bit quicker. Same thing with 13. Instead of plugging in 13, doing 13 minus 4, which is 9. The square root of 9 is 3. 3 times 2 is 6. 6 plus 3 is 9. You might have even noticed the pattern. So if I come over here and I graph all these points, I already did the first two, right? How about 8 comma 7? Bingo. How about 13 comma 9? Bingo. So I think that it's just as easy to take this table, the parent table, and just adjust it. And if you have your calculator at your house, you can actually set this into your y equals and go to your table. And don't mess around with finding the ones that say error or the decimals. Just go through and pick out the nice ones. Those nice ones are going to be the ones that were transformed to give you the real whole numbers. Last one. So here we have a cube root, right? And this is the parent function graph right here. These are our points that we normally plug into the regular cube root of x. So what we're going to do first, we're going to do our HK transformation, start with the X value transformations, and it says plus 2, so we're going to take 2 away from every single one of these. So take 2 away from -8 would make this -10. Take 2 away from that would make this -3. Take 2 away from that. Take 2 away from that. And take 2 away from that. Right? Now, just like we saw the last time, these y values right here, we're taking and multiplying them by -1/2, and then we're going to subtract 4. So really what we're doing here is -1/2 of the y from up here minus 4. So to do this quicker, I take, well, the real answer would be take this y -2, half of that would be it would be a +1 minus 4 would make this -3. Oh, come on. So this guy right here, if I put him in there, that would be +1/2 minus 4 would be -3.5. Take 0, 0 minus 4 is -4. What my kids telling you, if you can hear them, they're downstairs and watching Disney Plus or something. If I take the 1 right here and plug it in, that'll be -1/2 minus 4 will be -4.5. And you can probably see that this is kind of like a slope here going down by 1/2 every time. So I'm willing to bet this one would be -5. Okay, so if we go through ahead and plot all these on this graph, we're going to see that it was flipped across the x. So all the y's that are now flipped across the x-axis because of the negative in front of the 1/2, and they're also compressed at 1/2. They're compressed at 1/2. They're closer together, and they've been shifted 2 units to the left and 4 units down, right? So again, you can kind of see how getting the parent table and then adjusting these values is, I think, optimal. So we got this guy right here, which is -2, -4. We got -3 and -3.5. Yeah, that's there. It's a big dot. I gotta change the size of my dot here a little bit. Right? -10 and -3. Bingo. -1 and -4.5. Yep. And 6 and -5. 6 and -5. Now, again, you see the space between these points right here in our original parent graph is a full block. Down here, the space is 1/2 of a block because of that. Not only is it 1/2 of a block, but it's also rotated across the x. So instead of being like this one being up here, it's now over here. And that looks almost like a reflection across the y, but it's not. It's because of the fact that it was translated also. It was translated 2 units to the left and then 4 units down. So technically it's this guy. That guy is that guy, right? 2 units to the left, 1, 2, 4 units down, 1, 2, 3, 4 units down, and then the compression of 1/2. All right, so if you guys need any more help with the transformations, the reflections, the compressions or dilations, please hit me up. I'll gladly hop on a Zoom with you. And I got to take care of these kids, man.